All right, let's go through this final part 3 review. Here we're solving equations, whether they be exponential equations or logarithmic equations. If we look here, it also tells us to round where necessary. So when we have integer values, we won't have to round. Let's take a look at this equation. On the left-hand side, we have a single term, 30. On the right-hand side, we have two terms. Terms are separated by addition or subtraction. So we need to get the term that has our variable by itself. So our first term here on the right-hand side contains our variable x, and we want to get that term by itself. So we subtract 3 from both sides. 30 minus 3 is 27, and 3 minus 3 is 0. So in this case, we most likely can see that we can rewrite each side with the same base. We can rewrite 27 as 3 to the third power, and if exponential functions are one-to-one functions, and that implies that if the numbers are the same and the bases are the same, the exponents must be the same. So we have solved this equation. If you check by substituting back in, 3 to the third power is 27, and 27 plus 3 is 30. So we haven't made any mistakes. On the next one, we have 216 raised to some powers equal to 36. So we may be able to get these to have the same base. If you can't see that, then go ahead and take the log of each side. But I believe that 6 to the third power is 216, and I can rewrite the left-hand side. I can rewrite 216 as 6 to the third power. That is being raised to the x power. I can rewrite 36 as 6 squared. Now, on your properties of exponents, when you have a power to a power, you multiply the exponents. So this is 3 times x by the fact that exponential functions are one-to-one functions. If the numbers are the same and the bases are the same, the exponents must be the same. So 3 times x is equal to 2. Divide both sides by the coefficient in front of x. You're dividing both sides by 3. It's awfully easy. I see people all the time accidentally dividing both sides by 2, by the wrong value. Here's our answer for this problem. And again, if you check it, if you have 216 raised to the 2/3 power, remember that is asking you to take the cube root of 216 and now this exponent of 2, I can place it underneath the radical, or I can place it on the outside, and it's easier this time to place it on the outside. The cube root of 216 is 6, and 6 squared is 36. And that was the claim that the right-hand side would be 36, so our answer does check. All right, so here we have our variables on both sides, and so we really can't get the variable by itself. We cannot rewrite 12 as some integer raised to a power, nor can we write 10 as some integer raised to a power. So here I would take the common log of both sides. If I take the log on the left-hand side to balance the equation, I have to take the log on the right-hand side. Now remember that a common log, a base 10 is implied. By my power rule, when you have the log of some value with an exponent, as long as that coefficient in front of the log is 1, this exponent can move, and you can place it out in front as multiplication. So we have x times the log of 12. Now on the right hand side, whenever these bases are the same, it's going to be the exponent. In other words, 10 raised to what power is 10 to the x plus 3? Well, 10 raised to the x plus 3 power. So now I have my variables on both sides of the equation, but this time they're not exponents. Now I can move these terms. I can collect the x's on the same side of the equation. So I'm going to subtract x from both sides. So I have this term, and when I subtract x here, it goes away, so I have to subtract x on the other side. So remember, terms are separated by addition or subtraction. This first term has two factors, and we can write the second term as 1 times x just to help people out. Sometimes visually it's nice to put a coefficient of 1 in front of your variables. Now this term and this term have something in common. They have a factor of x in common. So we can factor out that common factor, and what's left in the first term is just the log of 12. And what's left in the second term is the 1. We almost have x by itself. We're almost finished with this problem. On the left-hand side, we have two factors. Factors are separated by multiplication or division. So we have x times this. We want to get the x by itself. So we're going to divide both sides of this equation. This time I'll write it out for you here. That by this quantity log of 12 minus 1. So when I cancel this out, I'm not canceling out the individual terms. I'm saying this entire factor. The number that's inside the parentheses is the same number that's inside the parentheses here. When you do that division, that equals 1. Alright, so on the right hand side, since I divided on the left hand side, I have to do the same on the right hand side to balance the equation. Alright, now I'm going to have to go to my calculator now because it wants me where necessary. There's not an integer value here. So I need to round this to the nearest thousandth, which is 3 decimals. So I'm going to fix my calculator to do the rounding for me. If you don't know how to round on your calculator, you can ask me. We can take a look at it and see. That way the calculator's doing the work and you're not making any silly rounding mistakes. Make sure you put parentheses around the entire denominator, and also make sure that you close the parentheses after the 12. So if I've keyed this incorrectly, and I believe that I have, I get to the nearest thousandth 37.888. Alright, so let's move on to the next one. On the excuse me, here we have a term on the left hand side. We have two terms on the right hand side. Terms are separated by addition or subtraction. We want to get the term that has our variable by itself. So we need to add 14 to both sides of this equation. When you add 14 on the right hand side, they just cancel, and on the left hand side, when we add 14, we get 32. Now, in this problem, we can rewrite each base as some power of 2. 2 squared is 4, and 2 to the 5th power is 32. So you may have to do some scratch work to recognize that. Maybe you need to come over here with 32 and recognize, well, 32 is 16 times 2. 16 is 2 times 8, and 8 is 2 times 4, and 4 is 2 times 2. So you have 1, 2, 3, 4, 5 factors of 2. 2 raised to the 5th power is 32. Now, the 4, that's easier to see, 2 squared. 2 times 2. When you have a power raised to a power, you multiply the exponents. Take this 2 and distribute it through this binomial. The 2 times 2x is 4x. Don't forget to distribute it to the other term, minus 2. Exponential functions are one-to-one functions. If the numbers are the same, and they're the same because of that equality, and the bases are the same, the exponents have to be the same. It's not correct to say that they cancel, although I know that's how students describe it. Let's add 2 to both sides and then divide by 4. This is referred to as a two-step equation. We add 2, that negative 2 cancels, add 2 over here and we get 7. And x is then 7 divided by 4. And I don't need a decimal approximation for that. I'm just going to, although that's not an integer, that is an improper fraction, and I'm just going to leave it like that. If you want to put it as a decimal, that's fine, but I'm just going to leave it like this. Alright, now our next one. 49 and 7. You can look at 49 and see that it's 7 squared. So we can write the same base on this. Now, if you didn't recognize that and you took the log of each side, you're going to get the same answer that we do. But you can probably do it just in a few more steps. It's easier, I believe, when you recognize that you can rewrite it with the same base. So the 49 is 7 squared being raised to the 2x plus 1. That's equal to 7 raised to the x squared minus 3. You have a power to a power, you multiply the exponents. If you have 2 to the 3rd power, and that's raised to the 4th, that's 2 to the 12th power. And maybe you can see that if you think this exponent has a base of 2 to the 3rd, so 2 to the 3rd is repeated 4 times. Now, a power to power you multiply. When you have multiplication, you simply add the exponents. 3 plus 3 plus 3 plus 3, you're going to get 12. If you came in and did this further, each 2 to the 3rd is 3 factors of 2. So if you expand it all the way out, you're going to see that you're going to have 12 factors of 2. But a power to a power you multiply. When you have 2 bases that are the same and you're multiplying, you add the exponents. If you think of a numerical example that might help you to remember that, oftentimes you see too many people adding these exponents, and that's incorrect. You need to multiply. By the fact that these exponential functions are one-to-one functions, if the number's the same and the base is the same, the exponents have to be the same. So this equation, they say that it is quadratic in x, that you can see that x is being raised to the 2nd power. Whenever you have a quadratic equation, get it in standard form. Get it in the form ax squared plus bx plus c. From there, attempt to factor it, and if it cannot be factored, use the quadratic formula. The quadratic formula takes the opposite of b, plus or minus the square root, and what's underneath the square root is referred to as the discriminant, and it's b squared minus 4ac. The discriminant does not include that radical. That's the numerator, and all of this is being divided by 2a, and that will provide you 2 solutions to this equation. It has a degree of 2, so there's 2 solutions. One is when you're adding, the other is when you're subtracting. Alright, so let's come back to our equation and get it in standard form. Let's subtract 4x from each side. When we subtract 2 on the left-hand side, it's 0. When we subtract 2 over here, it becomes minus 5. Now, I believe on this one that we can factor it. We won't have to use the quadratic formula, but it's fine. If you don't recognize that it can factor, the quadratic formula always works. We've got x minus 5 times x plus 1. If two numbers have a product of 0, then either the first number represents 0 or the second number represents 0, which this splits into two equations now. Add 5 to each side. We've got x equals 5. Subtract 1 from each side, and x equals negative 1. Those are the two solutions. Either one of these values, if you plug it in on the left-hand side and calculate that value, plug the same value on the right-hand side, those numbers will be the same. Alright. Our next one is not an exponential equation, it's a log equation. On the left-hand side, we have two factors. We've got this 6, and then it's being multiplied by this other number, and this number is the natural log of x plus 4. So we need to get the factor that has the variable by itself, so we need to divide both sides of the equation by 6. Here, since that's multiplication, the 6 divided by 6 is 1. We have the natural log of x plus 4. Now, we're going to let the calculator do the work, so some people may not reduce that fraction, but I can't resist. These are both even numbers. Half of 40 is 20, and half of 6 is 3. Now, also remember that ln stands for natural log, but students can think of this as log base e. So every logarithm has a base associated with it. This base e occurs so often, and I'm not exactly sure how the notation changed, but apparently to make it stand out versus the other logs, they write ln, not nl, natural log, but ln. So we need to convert this from a log equation to an exponential equation. Okay, the base is e, and this base has some exponent associated with it. Well, the pattern is that a log will always equal the exponent. So this e, which is like pi, it stands for 2.718, blah blah blah, it goes on forever, just like pi 3.14. This e is an irrational number, but anyway, the base e is being raised to 20 over 3 power, and that equals my argument x plus 4. Well, this may be an ugly number, and we can let the calculator give us a decimal approximation for it, but the x plus 4, it's pretty easy to get x by itself. Just subtract 4 from each side. So we've got this e to the 20 over 3, and we're going to subtract 4 from it. And when we subtract 4 here, 4 minus 4 is 0. And I just wrote the x on the left-hand side. So I've gone as far as I can go with pencil and paper. I now need to jump to a calculator. And remember, we're rounding to the nearest thousandth, which is 3 decimals. That on most calculators, this e can be found on the natural log button, but you have to hit your second key, or sometimes referred to as a shift key, that on these Texas Instruments is the upper left-hand corner. So if I press that second and then press LN, on my calculator it gives me that base of E, and it also is ready to accept the exponent. Sometimes you'll have to hit an up arrow, referred to as a caret key, to key in the exponent. But I have 20 divided by 3. I need to close that parenthesis to tell it I'm through with the exponent, and then subtract 4. And to 3 decimals, the value that I'm getting for this is 781.772. All right. Here we have a log equation. We have two terms on the left-hand side. They're both logarithms. On the right-hand side, we just have the constant of 1. We have our properties of logarithms. You'll have a reference sheet that tells you that if you have the log of A plus the log of B, that's equal to the log of A times B. Now, that equation on your paper, I believe, is actually written in the reverse order, that you have log of AB, A times B, is equal to log of A plus the log of B. Equations have that property that they're reflexive, that you can change the size. Is that reflexive or symmetry? Might be symmetry. Anyway, it has this property that you can switch the sides. So let's use that we can write these two logarithms as a single logarithm. So I have log base 8, and now I'm going to multiply these together. When I take this x and multiply it by this binomial, I'm going to go ahead and distribute it now. So x times x is x squared minus, and then the 7 times x. This is equal to 1. So I've gone as far as I can go with trying to get the variable by itself. I can now change this log form to an exponential form. The base is 8. A logarithm equals the exponent. The exponent on this 8 then is 1. And this is x squared minus 7x. This is a quadratic equation. We want to get it in that standard form like we were talking about on that previous problem, and then attempt to factor it or use the quadratic formula. If I subtract 8 from both sides, and again, it appears to me that we'll be able to factor this. If you don't recognize that, you can still use that quadratic formula. And remember, the quadratic formula is a fraction where the numerator is the opposite of b plus or minus the square root of the discriminant, and the discriminant is b squared minus 4ac all over 2 times a. So if we factor this, we get x minus 8 times x plus 1. By the zero product theorem, if two values have a product of 0, then one or both of the factors must equal 0. So x minus 8 equals 0, or x plus 1 equals 0. So we're getting solutions of 8 or -1. Now, for these logarithm equations, we have to check for extraneous solutions. We have to plug this back in to the original equation, and we need to avoid taking the log of 0 or the log of a negative number. Now, I'm not saying that we have to avoid negative answers. I'm saying that when you plug that value in, you have to be taking the log of a positive value. If I plug in 8, 8 minus 7 is positive. And the log of 1 with any base is just 0. And log base 8 of 8 is 1. This one checks. If you plug in a -1, a -1 minus 7 is the log of -8. Or over here, the log of -1. And our domain is positive real numbers. We can't take the log of a negative number. This is referred to as an extraneous solution. So it doesn't satisfy the original equation, and our only solution is x equals 8. All right, again, we have a log equation. So again, we've got to check our answers just like before in that previous problem. We have we have the term that contains our variable by itself. We've gone as they've presented it to us as far as you can go with normal operations on equality. The inverse of this logarithm is an exponentiation. So we need to change from log form to exponential form. The base is 6. A logarithm equals the exponent. 6 raised to the third power is equal to 10x plus 6. This is just a linear equation. It is not quadratic. We have an exponent of 1. All we have to do is get the x by itself. 6 raised to the third power we've seen in a previous problem, 216. So this is a two-step equation. To solve for x, we take this 216 and subtract 6 from it and then divide by 10, and we should get 21. Let's come up here and plug that in. 10 times 210. 210 plus 6 is 216. 6 to the third power is 216. This is our solution. Mainly when I was plugging it in, I was trying to make sure that I'm not taking the log of a negative number or the log of 0. Alright, so again we have an exponential equation, or excuse me, a log equation, and we want to change it into an exponential form. We have a base of 3, and the exponent is also 3. That equals this quadratic expression, x squared minus 5x plus 3. So 3 to the third power is 27. We need to subtract 27 from each side to get this in standard form. 27 minus 27 is 0. And 3 minus 27 is a negative 24. So we can factor this. We have x minus 8 times an x plus 3 gives us possible solutions of x equals 8 or that x equals negative 3. So the 8, let's plug it in. 64 minus 40, 24, plus 3, 27. 3 to the third power is 27. This checks. Let's plug in a negative 3. And here we'll take a little bit more time to demonstrate the arithmetic. X squared means negative 3 squared. If you're keying it in a calculator, the parentheses are important. Minus 5 times the negative 3, then plus 3. So negative 3 times itself is a positive 9. Negative times the negative is positive. And then plus 3. 9 plus 15 is 24, and 24 plus 3 is 27. So again, this checks because 3 to the third power is 27. So this time, even though, see, this is a great demonstration that I'm not afraid of negative answers. This negative answer did not make my expression negative. It was a positive 27, and I can take the log of a positive value. I am not afraid of negative answers. I am afraid of taking the log of a negative number or the log of 0. Alright, we're back to an exponential equation. The 70, I can't write that as a power 7 raised to some power. So I can't get the bases to be the same. To undo this exponent, I'm going to have to take the log of each side. And I can take it the common log button or the natural log button. I'm going to choose one of those two because most likely I'm going to have to go to the calculator to get a decimal approximation, and the calculator only has a common log button and a natural log button. So although I could take the log base 7 of each side, when I get to the end I would have to use the change of base formula. It's going to be easier for me and more calculator friendly to just take the common log of each side. Let's take the log of the left hand side. To balance the equation, we take the log of the right hand side. I'm not going to go to the calculator yet because I'm going to wait that until my final expression so I don't get any round off error. by my properties of logarithms, this exponent comes out in front. When I move this exponent out in front, I need to have parentheses around it because this entire exponent is multiplied by this log of 7, not just one of the terms, but both of the terms. So on the left-hand side, I have two factors. Factors are separated by multiplication or division. And in my first factor, I have two terms. That's the term of interest, this x. I need to get this x plus 4, this factor, by itself. I need to divide both sides by the log of 7. And log of 7 divided by log of 7 is just 1. Now remember, this does not mean log times 70 or log times 7. I can't simplify the 70 over 7. You just can't. It's not multiplication. It's a function. To get the x by itself, we'll subtract 4 from each side. So the 4 minus 4 is 0, giving me just x on the left-hand side. And this fraction may not be your favorite fraction, but it does represent some number, and you're going to subtract 4 from it because when we subtracted 4 from the left, we also have to subtract 4 from the right. So we're going to have to go to the calculator to get a decimal approximation for this number. When you key it into the calculator, you have to be careful to close the parenthesis after the 70, so you hit log 70, hit the parentheses, divided by log of 7, close the parenthesis again, and then minus 4. So I get negative 1.817. With exponential equations, I'm definitely not afraid of negative values, and I don't have to worry about extraneous solutions either. So this, if we've done our calculations correct, this is going to be a correct solution. Alright, so now on the left-hand side we have two factors, 2 times this e raised to the 3x. So this is an exponential equation. We need to get this e to the 3x by itself, so we'll divide both sides of this equation by 2. The 2 divided by 2 is just 1. We have this e to the 3x is equal to, well, half of 64 is 32. Now, we can't write this with the same base, so we're going to have to use logarithms, which is the inverse of this exponential. Now, this is one time as well that we're going to be smart and use the natural logarithm of each side. Remember, the natural log is log base e. Since this is base e, it's going to be better and easier if we take the natural log of each side. All right, so the natural log of the left-hand side, then to balance the equation, natural log of the right-hand side. This, again, this ln can be thought of, or you could even write it as log base e. And we have seen before that when you have this base and this base being the same, that this just simplifies to the exponent 3x. Or, remember, this logarithm is equal to an exponent. E raised to what power is e to the 3x? Well, e to the 3x is equal to e to the 3x. This left-hand side is 3x. The right-hand side, just natural log of 32. To get x by itself, we divide each side by 3. Go to the calculator, the natural log button. After the 32, close the parentheses. Our calculator is fixed to 3 decimals. That's to the nearest thousandth. So I get 1.155. And hopefully you get the same. All right. Again, we have another exponential equation, and this one's a little bit tougher. You know, we see we see on the left hand side a fraction, and that our variable is in the denominator. So we've got to try to get that term that contains our variable by itself. I'm going to look at this 7 as 7 over 1. This equation now is referred to as a proportion, and a common technique in solving a proportion is to cross multiply. Students seem to like cross multiplication, although they use the phrase cross multiplying when it's really inappropriate. That here we have an equal sign, and you can see we've crossed over that equal sign. That's cross multiplication. Just because you have a fraction, or just because things in the numerator and denominator are canceling, does not mean cross multiplication. Alright, so along this gray diagonal we have 7 times the binomial 3 plus e to the negative x. And along the yellow diagonal we have 100 times 1. On the left hand side we have two factors. This second factor has two terms, and it's this term that contains my variable that I want to get by itself. So first I get this factor by itself by dividing both sides of the equation by 7. And 7 divided by 7 is 1. So I have this 3 plus e raised to the negative x power. And again, I'm not going to go to the calculator yet. I'm just going to let it be 100 over 7. I don't want to have round off error in my answer. So these two terms, the e to the negative x is the term I want to get by itself, so I subtract 3 from both sides. 3 minus 3 is 0. This 100 over 7 minus 3. Now, I can let the calculator do the work. I don't necessarily have to get a common denominator and subtract those. Although I suppose it's good practice. If we rewrite the number 3 with a denominator of 7, we multiply by 7 over 7. So we're just multiplying that number by 1. When you multiply or divide fractions, it's pretty easy. To multiply fractions, you just take the product of the numerators and the product of the denominator. 3 times 7 is 21, and 1 times 7 is 7. So, with the same denominator, we can now just take 100 minus 21, which I believe is 79. And now, since this base is e, we'll take the natural log of both sides. The natural log of e to the negative x is equal to the natural log of my fraction. And since this is base e to what power is e to the negative x? Well, that's negative x. And multiply both sides by a negative 1, and you'll have x by itself. So we go to a calculator and take the opposite of the natural log of 79 over 7. Let's see what we get. I get negative 2.424. Hopefully you got the same. Alright, our final problem. Now, don't freak out. This is a word problem, but it's a very easy word problem. I don't have to necessarily draw a picture or think this through a lot, because all I'm going to do is just plug in a number into this function. But let's take a look at it and see if we can't understand a little bit what's going on. The velocity of a skydiver after jumping. So you've got some plane, and from this plane you have a sky jumper that is jumping out of the plane, and hopefully the parachute opens and the person comes down to the ground, and that their velocity is not going very fast when they touch the ground. Alright, So let's take a look. It says the velocity of a skydiver in feet per second, t seconds after jumping is given by. So the person jumps out of the airplane, and then 1 second goes by, 2 seconds goes by, 3 seconds goes by. Well, this equation talks about the velocity of the skydiver as they jump out. So it wants to know after how many seconds will the velocity be 60 feet per second. So I lied a little bit. We're not plugging something in. This 60 feet per second is the velocity. It's the left-hand side of this equation. So at what point is the person's velocity, how many seconds after they jump out of the plane will they slow or to 60 feet per second? So on the left-hand side, we've got 60, and on the right-hand side, 90 times 1 minus e to the negative 0.21 t. All right, so on the right-hand side, we have two factors. It's the second factor that has our variable. Let's get that factor by itself. Let's divide both sides of this equation by 90. 90 divided by 90 is 1, and now I just have my two terms, 1 minus e to the negative 0.21 t. On the left-hand side, the powers of 10, the zeros cancel. 6 over 9 just reduces to 2 over 3. Alright, I'm going to erase my ground to have a little bit more room to work with. Alright, so these first two terms, these two terms here, I want to get the term that has the variable by itself. So let's subtract 1 from each side. We've got 2/3 minus 1. I'll write 1 as 3 over 3, and 1 minus 1 is 0. Now don't forget that negative sign, and we've got this. So 2/3 minus 3 over 3 is a negative 1/3. And on this side I have a negative value. If I multiply both sides of the equation by negative 1, then it'll get rid of these negative signs. The opposite of negative 1/3 is positive 1/3, and taking the opposite of the right hand side, we get e raised to the negative 0.21 t. Alright, so now let's take the natural log of both sides, because we've gone as far as we can, and this is an exponential equation, and to undo that exponent we need to take its inverse, which is a logarithm. So if I take the natural log of 1/3 on the left hand side, I have to take the natural log of this e to the negative 0.21 t. Now remember, this natural log is base e, so you have base e and a base e, so that means that the right hand side simplifies to this exponent, to negative 0.21 t. Now, in one more step and we're done with this problem. Let's divide both sides by negative 0.21. So I'm going to write my t on the left hand side. If I divide this side by negative 0.21, that cancels, that's just 1. If I divide this side by negative 0.21, I'm now going to let the calculator do the work. So if I key in my numerator the natural log of 1/3, close that parenthesis after the 3, divided by, and now in parentheses I'm going to put negative 0.21, and you should get 5.213. And remember, that's in seconds. So in just a little more than 5 seconds after you jump out of the plane, the skydiver is traveling at 60 feet per second, not 60 miles, per hour or per second. You do have to pay attention to the unit, 60 feet per second. All right, so that's the last problem, and I hope this helps. Talk to you later.